Hi everyone, I'm Sivalakshmi, working as an assistant professor in EC department at R.M.K College of Engineering and Technology. In today's video, we are going to see about logic gates. So what is logic gates? As I've mentioned in my previous video, they are the basic building blocks of any digital systems. And it is an electronic circuit having one or more than one input and only one output. Here always the relationship between the input and the output is based on a certain logic. So based on this only we have logic gates named as AND gate, OR gate, NOT gate and so on. Here the very first application I can quote is your flip-flops. Here for an example I've shown you SR flip-flop with NAND gates. Whereas a detailed study on this could be done during your third unit of your syllabus. So I'll explain this in detail during those videos. We'll move on to the next. Types of gates available. As you know, the basic gates are AND, OR and NOT. Also you have something called universal gates, NAND and NOR. Why they are named as universal now? Using these two gates, either NAND or NOR, you can build your AND or NOT gates. So this is the reason behind why they are called as universal. And also you have two more gates which are named as your special gates or the derived gates. So we will see each of the gates in detail. So we will start on with basic gates. Remember that under each gate we will see their function, truth table, symbol of it, switching circuit and also the ICs and their pin diagrams. So first comes is your AND gate. So what is the function of it? It performs its logical multiplication, as you all know already because you would have come across in your 12th standard syllabus. Few of your, if you're CBSE, it's for sure. So next we will see the truth table because truth table is nothing but it gives you the input and output relationship of a gate. So even with the help of your truth table alone, you can identify what is that circuit is all about. So coming to the truth table, as I've told you, this AND gate is going to perform your logical multiplication. So when you're performing your multiplication, you can have a high output only when all your inputs are high. So look at the truth table, it is evident. So only when both the inputs are high, you will have a high output to be produced. For all of the combination, you will have a low output. And this is a symbol of your AND gate and this is your logical expression. Logical expression is nothing but your output. It speaks about your output. Q is equal to A into B. And next comes is your switching circuit. Here I have taken two switches A and B. So whenever they are closed, it means it is high logic. Whenever they are open, it is low logic. And here the output is your bulb. Look at this working. So when both my switches are closed, I have the high output. That is your bulb is glowing. For all other combination of inputs, your bulb is not glowing. Even with this simple circuits, you can make the analogy with your gates. So that is why your logic gates is also at times called as your switching circuit. So next comes your IC. So what is the IC used for your AND gate now? IC 7408, which this number you will come across in your laboratory, analog and digital laboratories. So this will be very useful and you have to by heart your pin diagram. Only then you can give your connections. You have to remember which of the pins are your inputs and which are your outputs. So here look at the pin diagram of your IC and IC 7408. Within one single IC, I have 4 gates enclosed. So always remember your 7th pin is going to be ground and your 14th pin is going to be your positive of your supply. And remember your pin number 1, 2, 4, 5, 9, 10, 12, 13 are always going to be your inputs. And your outputs are pin 3, 6, 8 and 12. So you have to by heart this, no other go. So remember this, when you come to your laboratory, you have to come with this pin diagram. Only then you can make your connections. So Just as an added information, I have been providing this within this slide. So next we will move on. Comes is your OR gate. What is the function of your OR gate now? It performs its logical addition. So it is also evident from their truth table. Whenever any one of your input is high, or when all my inputs are high, I'll have my high output logic to be produced. Otherwise, the output is 0. So this is the truth table of your 2-input OR gate. And this is the symbol of your OR gate. And the logical expression which speaks about the output is C is equal to A plus B. Here the operator is plus, remember. So next comes your electrical circuit. Even with that, we can make the analogy of the same function. Look at this, wherein in your AND gate, we connected the switches in series, wherein here we have connected the switches in parallel. So only when you make this sort of connection, you will have the function OR gate to be performed, else it will perform your AND gate. So remember, your switches has to be parallel. So look at this, as I've told you, when any one of your input is high, I have a high output. So look at this, when any one of my switches are closed, my bulb is glowing. Here the output is your bulb. So you can have that. Next comes is your IC. IC 7432 is your OR gate IC. Within this IC, you can see 4 OR gates to be encapsulated within a single IC. And this is also a 14-pin IC. And always, as I've told you, 7th pin is going to be your ground and 14th pin is going to be your positive of your supply. And remember, the pin 1, 2, 4, 5, 9, 10, 12, 13 are going to be your inputs, and your pin 3, pin 6, pin 8 and pin 11 is going to be your output. So remember, this is for purely for your laboratory purpose. When it comes for implementation, you have to remember the basic IC numbers and the pin diagram. Only when you connect it in this way, you'll have the outputs to be seen. If you give an output wire to be connected to either 2 or at times it will get a short circuit or it won't perform its function properly. Next we will see here is a NOT gate. So coming to the function, it performs the inversion operation. That is, whenever your input is 0, you'll have output to be 1, or whenever the input is 1, you'll have the output to be 0. So this is the symbol of your NOT gate. Look at this, it might look like your diode symbol if you put a straight line over here. So remember, you have to put a bubble over here. Then it becomes a NOT gate. Here the input is A and the output is C. So the logical output expression of this gate is C is equal to A bar. So this is the truth table and symbol. Next comes is your electrical switching circuit. Here also we can have a circuit which can make an analogy with their NOT gate function. So remember, so far what we have made is we have connected both my circuit in series with the output, wherein over here you have to connect your switch in parallel with your load. Here this is not a GIF image. You have to assume it works like this. So whenever my switch is closed, you'll have a low output to be produced because at this point it would be grounded. So you'll have your supply to be grounded. Whenever it is open, whenever the switch is open, this will make as a full circuit. That means your electrons will flow through this wire and you will have the load to be glowing and you will have a high output to be produced. Whenever your switches are closed, this will make a closed circuit and you will have your electrons to be grounded. So you won't have your load to be glowing, or you don't have your load to be producing an output. So this is the logic behind your NOT gate. Next comes is your pin diagram. So here IC 7404 is your NOT gate IC. Within this IC, because remember you have always your NOT gate is with your single input and single output. So you can enclose 6 NOT gates within a single IC. So this is the way you have to make the connection. Remember the pin diagram and the pin number, pin numbers as well as the IC number. So altogether you have 6 inverters, in other words, within a single IC. So always here also 14 pin to be a positive of supply and your 7th pin to be grounded. So this is all about your basic gates. Next comes is your universal gates. What are universal gates? As you saw it already, it is of two types, NAND and NOR. So those two gates we call it as a universal gates. And also we mostly prefer universal gates more than your basic gates. First we will see what are universal gates and why the name. They call it universal because they are able to replace all your basic gates. That's the reason. And why we prefer now, in a circuit the number of ICs used will be reduced. In turn, space, size and cost of the circuit would be reduced. So this is the reason behind why we thrive and drive towards your universal gates into your circuits. And I'll justify the same with a sample example circuit after explaining your NAND and NOR. So first we will see NAND gate. So what is NAND gate? It is nothing but combination of two gates together. Your and your NOT together is your NAND. So what is the function of it now? It will perform your inversion operation of your AND gate. So in evident to that we'll have the truth table also. Look at the symbol first. As I told you, it is a contraction of your AND as well as your NOT. Here NOT is symbolized with the help of your bubble. So whenever there is a bubble in your logical circuit, now it is understood it is performing a inversion operation. So this is the symbol of your NAND gate. And this is the logical output expression of your NAND gate. C is equal to A dot D the whole bar. And even look at the truth table as I've told you. When both my inputs are high, I'll have a low logic output to be produced, which is a inversion operation to your AND gate. And similarly for all other cases, you'll have a high output. And we will see even this with the help of your electrical switching circuit. Look at this. Here we'll have a circuit, that is your lamp. One end is connected to your supply and the other end is grounded. And in parallel to the lamp, you'll have, that is to the load, you'll have your switches in series connected to the load. So as I told you, NAND is nothing but it's a contraction of your and your NOT. So look at that. Even this circuit should satisfy both the condition. Here I have the condition. What is the condition for AND gate? The switches has to be in series. It is series. And for NOT gate, the switches should be connected in parallel with your load. So it is both my switches are in series, whereas in parallel with your load. What is your load? No? Your lamp. So before moving to the explanation, assume whenever the switches are open, it means logic 0. Whenever switches are closed, it means logic high. Similarly, whenever lamp glows, that is on, then it is high logic. Whenever it is off, it is low logic. So with that assumption, we'll go on to the explanation. Look at this. For the first case, I'll explain. When both my switches are open, in other words, when both my inputs are 0, what happens to my output? Actually speaking, I should have a high output. That is, your lamp should be glowing. So how is that possible? Because if both the switches are open, this path will act as an open path. So in other words, as soon as I supply the voltage, you will have the electrons to be flowing through this wire. Since this is an open path, you will have all your electrons to be flowing over here and a voltage drop across will happen across your lamp and your lamp will be on. So I've satisfied my first condition. And what is the next condition? When either of my input is high, my output has to be high. So if either of the switches are closed, then output should be high. Yes, even for that case it will satisfy. When either A or B are closed, even at that time, this path will be an open path. So similarly I'll have the same condition to be arise. All my electrons will be flowing through this path And then I'll have a voltage drop across the lamp since your lamp will be glowing. Coming to the last condition, I've told you, when all my inputs are high, that is when both my switches are closed, remember this will act as a closed path. So in other words, it's a tendency of the electrons that it will move fast across a closed path. So this will act as a circuit and you will have all your electrons to be flowing through this path and it will get grounded. Even at times, practically speaking, you'll have electrons to be flowing through this path also, but it won't be enough to for your voltage across your lamp to be flowing. So I can say that it satisfies all my four conditions so that I can make an analogy with this circuit. So coming to your IC. So what is the IC used for your NAND gate now? It's nothing but IC 7400. IC 7400. So here also you will have four NAND gates within single IC. So you'll have the 14 pin, as usual, 14 pin to be your supply and your 7 pin to be your ground and the remaining pins contributing for your inputs and outputs. So this is what all about your NAND gate. So next we will move on to your NOR gate. So what is your NOR gate? So as the name speaks, it's a combination of both your OR gate and your NOT gate. So it is also evident from the symbol and the truth table. Look at that symbol. You will have your OR gate in contraction with your NOT gate. NOT gate could be symbolized with your bubble, right? So this is, as on whole, this is the symbol of your NOR gate. And this is the output logic expression. C is equal to A plus B the whole bar. Remember, it should be the whole bar. And coming to the truth table, as I told you, it speaks about the input-output operation. Here I should have the inverse operation to your OR gate. So what is your OR gate? When either of the input is high, I'll have my output to be high. Wherein, look at this, when both my inputs are low, I'll have a high logic. For all other cases, low logic. The inverse operation of your OR gate. So we will see with an example, that is your switching circuit, electrical switching circuit. Even in the circuit, we can see it satisfies both your OR condition and your NOT condition. For your OR condition, I told you that your switches has to be in parallel. Yes, it is parallel. Whereas for NOT condition, the switches as on whole, it should be in parallel with the load. Yes, it is. So now going for the explanation, making all your assumptions as I told you earlier, we'll go into it. So what are the cases available? When both my inputs are low, my output is high over here. How is it possible? When both my inputs are low, that is, when both my switches are open, what will happen? This path will be an open path. So in other words, as on whole, this will be a closed circuit. So as soon as I supply, all your electrons will be flowing through this path and a voltage drop will occur because your lamp will be glowing. And for the other case, when either of the switches are closed, my lamp should not glow. So what will happen, you will see, when either of the switches are closed, look at this, when this is closed, when A is closed, B is open, assume that this will be a closed path, right? As I've told you, the tendency of the electrons would first start flowing through your closed path. So if the electron starts flowing through this A now, then all your electrons, most of your electrons will get grounded. And similarly for the other condition, when A is open, B is closed now, the same will happen. So in other words, you won't have enough electrons to trigger your lamp on. So this is how you'll have the output to be 0. When both my switches are closed, what will happen? Because remember, when both the switches are closed now, then this will become a fully closed path and you will have, it's for sure that you will have most of your electrons would be grounded. So even for that case also, you don't have your lamp to be glowing. So this is how I can relate and I can make an analogy with your NOR gate function. Next we'll have your ICs. What is the IC used now? Remember the pin number IC 7402 is used for NOR function. Look at this. See, so far what you have seen is all your gates inside this IC would be facing downward, wherein only for NOR gate, that is specifically for IC 7402, you will have all your four gates to be facing upward. Remember, that is, your input output pins will be changed. So this is a very important point. You have to make note of it and remember while coming for your laboratories and while doing experiments. Then else your IC will be wasted. So here the output pins will be first pin, fourth pin, 10th pin and your 13th pin, which was your inputs in your other gates, which was your inputs in your other ICs. Remember, these are the changes here in your NOR IC. All your gates inside encapsulated will be facing upward. So you have to remember this diagram. The pin number is IC 7402. So this is all about your NOR gate. So as I've told you, justification. How am I saying these universal gates are preferable than your basic gates? See, for an example, I have taken the sample logic circuit. This is a sample circuit. I need not go in deeper, but I'll explain you everything in detail how we can achieve the same in your later classes. But for explanation, justification purpose, I have taken this circuit. Look at the circuit. You have what are the basic gates available in the circuit? And, or, and not. So three gates are used within this single simple circuit. In other words, when you want to implement in your breadboard, now you need three ICs because only each and every ICs could provide you at least one gate which you want right now. So remember, three ICs are needed and also remember the size it is going to occupy in your breadboard. Whereas I'm saying that if I'm trying to implement using your universal gate, for example, NAND I've chosen. Now fully NAND, I can implement this. This circuit can perform the same which this can perform. Perform. So coming to this, look at this. How many ICs I would require for this circuit now? Look at this, 1, 2, 3, 4. This 4 I could implement with single IC because remember your IC 7400 encapsulates 4 gates and similarly the remaining 3 could be encapsulated in your other IC. So as to implement this I need only 2 ICs, whereas this basic using basic gates now I need 3 ICs. Similarly, even if I'm trying with fully with your NOR now, then I'll have the same. Look at this, the same circuit implemented using NOR implementation. So here also 1, 2, 3, 4. One IC is over, and then 1, 2, 3, 4. With the help of another IC, that is totally 2 IC. With the help of 2 ICs, I can implement the same circuit. In other words, the size of the circuit I'm consuming in the breadboard is reduced. So the cost would be reduced, the supply would be reduced, the heat generated would be reduced. So that is why people always thrive and drive towards your universal gates. I hope you would have had a better understanding with this example. Comes is your special gates. So sometimes they call it as a derived gates or at times special gates. So what are they now? As you have seen it already, they are nothing but your XOR gate and your Xnor gate. That is exclusive OR gates or exclusive NOR gates. So next comes is your exclusive OR gate. At times they will write it as your EXOR or sometimes just simply XOR like this. So this gate performs the operation, that is, it will produce a high output whenever your inputs are different. Whenever your inputs are different, you will have a high output logic. For other cases, you will have low output logic. So this is the logical function of your XOR gate. So this is a symbol of your XOR gate and the output logic expression is your C is equal to A XOR operator B. That is your A XOR B. This is the operator symbol of your XOR. So these are your different forms of your Boolean expressions. Always remember this is mostly used for simplification purpose and all. Whenever you see this expression, you can just simply replace with your A XOR B. That is A dot B the whole bar, sorry, A dot B bar plus A bar B. So this expression we call it as a XOR. So I can explain the same with your electrical switching circuit. You have to make the connection in such a way like this. It should appear. So look at this. Since already I have given enough explanations about your switches, series and parallel connections, I'm straight away going into the implementation. Just listen. Whenever your A is 0, na, your A bar would be 1 and B is 1, na, B bar would be 0. That is, it will be the complement of it. So what are the cases I can have over here? Na? Say for suppose this is the case when all my switches are open. Na? So it is understood even if I supply, I'll have all my electrons to be stopped here itself because this is an open circuit. You don't have your load to be, that is your lamp to be glowing. So in other words, I'll have my output to be 0. This is a condition. Even for the case when all my, you don't have a case like when all my switches are closed. I can't say all my switches are closed because when this is closed now, it is understood this has to be open. Even for the same, when B is closed now, B bar would be open. So even for that condition, that is when A and B is 1, that is switches are closed now, your A bar switch and B bar switch will be open. In other words, your here you'll have a break over the circuit, so it will act as an open path. So you don't have your load to be blowing. So even for this condition, you will have a low logic output. Coming for this condition, when A is 0 and B is 1, when A is 0, that means this is open and this is closed. When A is 0 now, it's obvious that your A bar, this switch would be closed. And B is 1. So this would be open. So this and this will be closed. In other words, you will have a closed path like this. It will look like a cross coupling. And these two switches would be open and these two switches will be closed. So through these closed switches, you will have your electrons to be flowing. As soon as I supply, you will have your electrons to be flowing. And through this path, you will have your electrons to be dropping across the bulb and you will have your bulb to be glowing off. So there happens your voltage drop across the lamp. So this is how you'll have a high output. And similarly for the other case, when A is 1 and B is 0, when A is 1 means this is closed, so this is open. When B is 0, now this is open, this is closed. In other words, you will have a path for the electrons over here and then you will have the electrons to be flowing like this through this path and you will have a voltage drop across this. In other words, you'll have your low lamp to be glowing. So that is how I'm saying I could make an analogy with this function, XOR function. So I hope you would have understood. So next, as usual, we'll see the pin diagram and the IC pin number. IC 7486 is always said to be your XOR IC. Even within this IC, you will have 4 XOR gates to be encapsulated. Whereas this arrangement is normal like your basic gates. You will have all your gates within your IC to be facing downwards. So you need not have any changes over here. All other things are the same like your basic gates configuration. But then IC number you have to remember. Got it? So next we will move on to Xnor Gate. So what is the function of it? It implements a logical inversion of your XOR. It, it provides you the inversion operation of the XOR. That is, previously what you saw is when inputs are different, you will have high output. Wherein over here, you will have high input only when the inputs are same. So look at the truth table. When the inputs are same, you will have a high output. When the inputs are different, you will have low output. So this is the case and this is a symbol because it performs the inversion operation of your XOR. So XOR in contraction with your NOT gate gives you XNOR. So this is a symbol of it, and this is the expression for it. At times, you will also see the expression like this. So if you find any expressions while simplifying, you can just replace with this expression. That is your XNOR. So what is the expression for your XNOR now? Your output Y is equal to AB plus A bar into B bar. So even this I could explain with your electrical switching circuit, having the same arrangement wherein the assumptions I have made for the switches are different. Look at this. You will have your output to be flowing only whenever you will have an output only when you have AB and A bar B. In other words, only when those switches are closed, you will have a high output. That is your XNOR. And also remember, you can also rewrite this expression, that is inversion of your XNOR, like this, that is dot encircled. So this is also dot encircled, called as your XNOR operator. So remember this expression. So as I've told you, only these two combinations would contribute for your high output. So whenever A and B is closed, whenever these switches are closed, you will have a lamp to be glowing. And similarly, whenever A bar and B bar switches are closed, you will have your lamp to be glowing. In other words, whenever the inputs are safe, you will have your high output. For other cases, you will have a low output. So simply the assumptions are different over here, but the same arrangement I have made use of. And next comes is your IC. IC 74266 is your IC for Xnor Gate. Remember this always. And here you have the different configuration inside. Whereas the upper two gates will be facing downward and the lower two gates will be facing upward. This also you have to make note of it. Got it? All other cases, as you know, how the inputs would be arranged. So this is what. So you have to by heart this when you come to your laboratory. Remember IC 74266. The arrangement is different over here. The upper two gates would be facing downwards. The lower two gates would be facing upwards. So this is all about your XNOR gate. So I hope you would have had a better understanding. I know that you people know your gates already introduced in your schools. I hope even with the ICs and much more explanation, you'll have a better understanding. Thanks for watching.